On the issue of climate change, Arctic is going to play a very important role. Though, on the Earth, it is the equator that is going to be hotter than other regions. Going by extent of rise, it is at the poles there is going to be more rise. In terms of rise, there is going to be more compared to temperature rise at the equator. It means more changes are going to take place at the poles compared to the equator. This is what is called polar amplification. Polar amplification. Polar amplification. So polar amplification means any change in the net radiation balance, can be greenhouse intensification, tends to produce a larger change in temperature near the poles than in the planetary average. So more change here compared to the rest of the Earth system. It is not only about warming, but this is true of cooling also. So if the planet is going to cool, more cooling here compared to the equator. It means one very important region that is going to be affected more intensely is poles, this pole and this pole. But between these two poles, Arctic plays more important role because Arctic is closer to most of the land. Closer to Antarctic, there is much less land. So Arctic amplification plays a very important role. This report, Arctic Report Card 2021, released by National Oceanic and Atmospheric Administration, says Arctic has been warming more than twice of the Earth. Okay. What is the explanation of the scientists for this polar amplification? The explanations are somewhat complex, but some simple explanations include ice albedo effect. For example, in the pole, there is ice. As ice melts and ice is lost, ocean is going to be exposed to radiation. The difference between ice being exposed to radiation and the ocean getting exposed to radiation is when the ice is getting exposed, it reflects back. This is called albedo. As ice melts, there is less albedo and more radiation and more melting. One important law about global warming is that as there is more warming, it leads to much more warming. Okay, as the temperature rises, then more temperature will rise. As ice melts, more ice will melt. Because as ice melts, incoming radiation is more. So this is ice albedo feedback, which is true at Arctic level, at Antarctic level. And also lapse rate feedback. Lapse rate feedback means as now the ice is at a higher elevation. As ice melts, then elevation comes down. As elevation comes down, temperature comes down, and so more melting. So it means rate of melting increases as there is more melting. There is more melting because the temperature rises. So this is called lapse rate feedback. Both ice albedo feedback and lapse rate feedback are called positive feedbacks. What is meant by positive feedback? Positive feedback is a feedback that pushes a system towards the next one. So, for example, if something is pushed, and because it tries to return, because it is pushed, if it tries to return, this is a negative feedback. But something is pushed to move out of this system, then that is a positive feedback. Okay. So the feedback that tries to keep in equilibrium is a negative feedback. Feedback that tries to keep the system move towards a new equilibrium is a positive feedback. So what is called a positive feedback here are actually negative to the mankind, because ice albedo feedback and lapse rate feedback both contribute to more warming. Okay, but are these feedbacks the only reason why there is a polar amplification? That is not true. In more complex ways, ocean and air circulation also contribute to intensification of change at the poles. So it is not simply these feedbacks, but circulation. Circulation is about how heat is transferred from equator to the poles. So that also contribute to polar amplification. So this is about polar amplification. As a consequence of polar amplification, Arctic sea ice is melting. The Arctic Ocean. Ice here is melting. This is the data. Arctic sea ice reaches its minimum each September. September Arctic sea is now declining at a rate of 13% per decade. At a rate of 13% per decade. So, and relative to the 1981 to 2010 average. Okay, so so this is how Arctic sea ice is melting. And next is about what is happening in this area, Greenland. Greenland ice also is melting. Okay. Greenland ice sheet melting. But Arctic ice melting doesn't contribute to sea level rise, but Greenland ice sheet melting contributes. Why? Arctic ice is already on the ocean. So when it melts, it doesn't rise the sea level because it is already on the sea. Whereas in the case of Greenland ice, which is there on the land, when it melts, it contributes to sea level rise. And how much is it contributing? Proceedings of the National Academy of Sciences 2020 said that melting of Greenland ice contributed to more than half an inch of rising ocean water since 1972. More than half an inch, making it the largest contributor of new water into ocean every year. And quarter inch of the additional water, which is half, is in the last 8 years. It means rate of melting increased. This is some of the projections of our IPCC. Greenland's contribution to sea level rise in millimeters. Okay. So huge rise is possible. It's 2.5 centimeter rise, around 2.5 centimeter rise is possible by 2030. So this is about Greenland. But more serious problem is coming from what is called permafrost. Permafrost. What is a permafrost? Permafrost refers to permanently frozen ground. Within that, there is a soil, rock, or sediment frozen for more than 2 consecutive years. How is that frozen? It means there is ice in that. So it is ice plus some substances. And permafrost can be there on land as well as under the ocean. Permafrost is not confined to the land only. It can be under the ocean. And when it is on the land, it doesn't have to be on the top layer. Permafrost can start after other layers on the ground, which is something like, see this one active layer, and permafrost is under that layer. Okay, permafrost consists of large amounts of biomass and also decomposed biomass stored as methane and CO2. So what is happening is that, see, this is biomass, rock particles, and all kind of these things with ice is a permafrost. When the permafrost starts thawing, it's called thawing. It's not melting because when the temperature rises, ice melts. So you say the whole thing starts thawing. Ice melts, and biomass, rock, and whatever is there will remain. and if it has methane or methane related products, then some problems are going to rise, because as ice melts and certain microbes operate on biomass. Microbes operate on biomass and contribute to its disintegration, giving rise to CO2 or CH4. Okay. So permafrost thawing gives rise to methane and carbon dioxide. Methane and carbon dioxide. This has become a very serious problem in the Arctic, because permafrost region is a huge one. So this one, so darker purple means higher percentage of permafrost. So it's all permafrost regions. There is Greenland, there is Russia, Canada, Alaska. Okay. 24% of northern hemisphere has permafrost. Substantial part is in Alaska, Greenland, Canada, Siberia. And this permafrost is thawing. And what is the impact of this thawing? It's releasing carbon dioxide and methane. And methane emissions are coming from many lakes, because within those lakes are permafrost. And as it melts, the layers become unstable. So if a building is on the permafrost layer, then that building may be destroyed. The same way roads and many other constructions. So infrastructure destruction, because it's there on the layer, and then this sinks, the ice is out. So this leads to, if the building is here, then the building may turn like this, or simply bridge may collapse. So this is one. And as there is melting, it contributes to water at certain places, and sometimes creating floods, creating landslides. Okay. But how much is going to be the CO2 and methane from this permafrost thawing? It is here, there are different estimates, but scientists know that in the entire permafrost, 1600 billion tons of carbon is there. 1600 billion tons of carbon in the entire permafrost, which is twice as that in the atmosphere. So in the atmosphere, only 800 billion tons of carbon. We're talking about carbon, not carbon dioxide. And twice of it is in permafrost. So how much is going to be released through permafrost thawing is not clear. So it is here, you have different estimates. There are some conservative estimates. Okay. For example, one estimate suggests that 110 to 231 billion tons of CO2 equivalents, which is half of it of carbon dioxide and half of it from methane, will be emitted by 2040. And 850 to 1400 billion tons by 2100. 100 to 230 billion tons by 2040. So 100 to 230 billion tons by 2040. So it means from present 2020 to 2040, within 20 years, this much. Okay, this corresponds to 4 to 8 billion tons of CO2 equivalents in the period 2011 to 2040. Annual emissions of 4 to 8 billion tons. Most recently, 50 plus billion tons of equivalent of CO2 we are emitting now. Whereas according to this estimate, say 4 to 8, which even if you think it is around 10 billion tons. Okay, if you think it is 10 billion tons, it is 1/5 of it, around 1/5 of what is going on now can come from emissions from permafrost. So if not 1/5, it can be 1/10. So this is big enough. This is big enough, and this is going to rise to 10 to 16 billion tons of CO2 equivalents in the period 2011 to 2100. So it means, so in the higher estimate of 16 billion tons, so basically CO2 release from permafrost thawing is going to increase. Okay. And there is simply no localized solution to stop this problem. No localized solution. No localized solution. Because this is spread across huge parts of northern hemisphere, and you can't do anything. Of course, other than through reducing the global warming itself, which precisely is the problem. Okay, but then these projections give how methane or carbon dioxide emissions are going to contribute to the problem and how things are more difficult. But one important point here is that even these calculations are not included in carbon budget. Not included in carbon budgets. So carbon budget refers to how much more countries can emit within a particular target of 1.5 C or 2 C. Those budgets did not include these Arctic emissions, and if you include these emissions also, then the amount that the countries can emit will come out to be much less than what they would appear otherwise. Okay, so this is a big enough problem which is not included in the carbon budget. But there is even more serious problem. Okay, that serious problem is coming from this particular thing. Coming from permafrost in the continental shelves of oceans near Arctic, Kara Sea, Lethwi Sea, East Siberian Sea. The continental shelf here is very, very shallow. Very shallow, 50 to 100 meters. Okay. These shelves have permafrost. And underneath this permafrost, there is a sediment with methane hydrates. So, and sometimes, say for example, in East Siberian Arctic Sea has a 2 kilometers of sediments with high concentration of methane. So in these oceans, so across the shelves, you have sediments of methane hydrates. And as this ocean is warming up, as the Arctic Sea is melting, ice is melting and the ocean is warming up, this entire thing is warming. And because this is narrow, it is going to the bottom of the sea. So much so that permafrost is thawing, and then methane hydrate itself is getting is affected, and methane is being released. Methane is coming out like this at so many places on the shelf. In fact, the situation in the Arctic is that methane is coming out not only near the oceans, it's coming out in lakes. And more dramatically, methane mounds are there on land. See, this is a methane mound. This is a methane mound. Pingo is a mound of earth-covered ice that can reach up to 70 meters height and 600 meters diameter, caused by the buildup of methane in pockets of thawing permafrost under the surface. There are several areas, and more than 400 such mounds are found. So, this is on the surface, methane is built up, and then when the methane reaches more than what this can hold, this is simply bursting off and creating huge craters. So methane is there. Methane is coming out from wetlands. Methane is coming out from the land like this, and then it's coming out in oceans. Okay. And there is one scientist, Peter Wadhams, Professor Emeritus of University of Cambridge, who is a Arctic ice expert who made more than 50 expeditions to the poles and author of A Farewell to Ice, which is translated into many languages, says something very, very dangerous. He says that he makes an estimate of methane in the oceans, in the continental shelf. He says that under certain circumstances, methane can come out of this continental shelves, and that can be to the tune of 50 gigatons. 50 gigatons of methane is many times more than the annual emissions now, because annual emissions now is only 50 gigatons of carbon dioxide equivalents, not methane, because methane is much stronger. Methane has a warming effect of 80 times stronger than carbon dioxide, but over 20 years. So methane's duration is less, but many times powerful. But given the emergency of the situation, the duration doesn't really matter. So Wasam says that these 50 gigatons under certain circumstances, can be released within a matter of weeks and months, and this can contribute to the rise of 0.6 Celsius. So it means global temperature can rise by 0.6 within weeks or months. Okay. And these things are not at all considered in IPCC calculations. Vadam says that many scientists think that methane coming from continental shelf will not reach the atmosphere because it will mix with the ocean and it won't come out. But Gotham says that that is not true in the case of a shallow continental shelf, which is there in these seas. Okay. So there is a very real possibility, and in defense of Wadham's, long before, US Geological Survey has previously listed Arctic hydrates destabilization as one serious scenario for abrupt climate change. So it means there are others too who think that hydrate destabilization can pose a serious threat. So what all this means is that there are many scary possibilities, and we can never be certain that as we try to manage these our CO2 emissions, and if we manage better, then we have control over this process that we started. It's not true. Things are very uncertain. Many scary outcomes are there. As discussed before, certain tipping points may reach and then the cascade can be initiated. So that is the reason why even when IPCC says that these are the ways in which you can be within 2C or 1.5C, it gives probabilities. There is this % chance of remaining within this particular time range, temperature range, because things are very, very uncertain. And the difference among the scientists is about quantifying anything. For example, on this, some may think it is simply around a fraction of presented emissions, and some may think it is closer to an explosive situation. Why do scientists differ? Because there are no precise quantitative measurements of most of the geographical phenomena. For example, under what circumstances, at what temperature, hydrate stabilization will take place, and where will it take place, and how much methane will be released, and then what are the consequences. It may be easy to know the logical steps, but it will be very difficult to quantify those things. For example, it is like predicting weather. We are not able to predict weather in a particular locality without uncertainty, even if we are very clear about the physical process. So more risks and more uncertainties are there, and uncertainties here mean huge risks to mankind.